Next, what we are going to do is that we are going to use some results to define integration of an arbitrary measurable function. Okay, so for arbitrary measurable function, one might not always define integration. So you would figure out for what type of function we can define, and the class of measurable functions for which we can define will be would be able to define successfully. That class we are going to call as integrable functions. Okay. So let we have f from omega to r plus, that means non-negative. Okay, if we have such function f, then integration of f dp, okay, would be defined as supremum of integration of, say, fn of omega dp, okay, over omega, okay, where what is my fn? Fn is simple functions and converging, so it is increasing to f. Okay, increasing to f. So fn is simple functions, but they are increasing, the sequence increases to f. Okay, so I mean almost sure convergence. Okay, if they increase to f, and then for each and every fn I evaluate this integration, I can evaluate using the earlier formula, and then I would get a sequence of real numbers, because when I integrate this I would get a one particular number that would maybe real number or maybe plus infinity, so extended non-negative real number, and we get a sequence of that which is non-decreasing sequence, because fn's are increasing, correct? So integration will increase. Okay, so non-decreasing, and then we are taking supremum of that. So that makes sense, because it is a sequence of non-decreasing extended real valued sequence, and we are going to get the supremum, and whatever the supremum, we are going to call that as integration of f. Okay. Now one can ask, given a function f, can one always find out a sequence of simple function which really converges to f and increases and converges to f? The answer is yes. Okay, there are some constructions which I am not going into the details. So this is true that given any function f, a non-negative measurable function f, one can get such fn. Okay, I would also require fn to be non-negative. Okay, so non-negative fn. This is always true. Okay, so then by this line we have given a notion of integration of f when f is non-negative. So what happens for general when f is any real valued function? Then we can write down f in two parts, that is f plus minus f minus, where f plus and f minus both are non-negative. That means they could be 0 or more than 0. Okay, both are non-negative, but I would be able to do that. Okay, so I mean it's very simple. So one can ask that, okay, why what assures me of such decomposition? It is easy, because given a function f, you take the maximum of f and 0. Okay, that would give you f plus, and you subtract. So f plus is the choice is easy. It is, you just take f of x and 0. So whatever the value, you call that is f plus of x. Okay, and then after keeping that f plus, you define f minus as f plus minus f. Okay, simple, because this is when f is positive, then f plus is also positive. Okay, they would have the same value, they cancel and make it 0. And if f is negative, then minus f is positive, so this is giving me the positive part, but f plus is always non-negative, so I would again get f minus is non-negative. Okay, so f minus is non-negative, so this is the way. And then why should this be true? Because now if we put f on the left hand side and f minus on the right hand side, I am going to get exactly the same equation. Okay, So after decomposing f in these two parts, integration, and then we define what is the integrability, because as I told that for every measurable function we might not be able to define integration of f successfully. Okay, so we introduce a subclass, the integrable functions. So if both integration of f plus dp and integration of f minus dp are finite. Remember earlier as we told that, okay, given a function f which is maybe unbounded, some function, okay, I can have fn, okay, simple sequence of simple functions whose own integration might be infinity, say, okay, and then there is no hope that integration f would be infinite. Otherwise, sometimes, these are all finite, but the integration f are all finite, but they grow to infinity. Okay, so I can easily have infinite value for this integration. Now we look at only for those functions such that both these things are finite. Then we call that f, then f is called integrable. Then f is called integrable. Okay, f is integrable. And then for an integrable function f, integration of f dp is defined to be integration of f plus dp minus integration of f minus dp. Now you understand that why do we need this finite thing. Consider an extreme situation when both integration of f plus and integration of f minus are infinity. Then we are into the situation of infinity minus infinity. Okay, that makes no sense, correct? That makes no sense. So to avoid that thing, okay, we consider the cases where both are finite. Okay, one can actually also either of these is finite. One can put that is there is a little relaxed situation which we are not going to consider. We are going to consider only the situation both are finite. Okay, and then this is the thing, and then it implies that integration of mod f dp is equal to integration of f plus dp plus integration of f minus dp. Okay, good. Now we discuss what do we mean by convergence of integrals. Okay, convergence of integrals. Imagine, so we start with some examples. Okay, so start with some example. Consider a sequence xn of omega which looks like n times indicator function of closed 0 to 1 over n open. Okay, so this is function of omega and that is defined on closed 0 to 1. Okay, so on the unit interval we have this function xn, and the measure space we consider here say close 0 1 and the Lebesgue sigma algebra and the Lebesgue measure. Okay, that is the measure space, and then we find out the integration of xn on this interval 0 1. What would be its value? Its value is just the area under the curve. The height is n, the base size is 1 over n, so the area is n times measure of 1 over n, that is 1 over n. This is 1, that is for all n. Okay, now we ask that what happens if we put limit. So limit n tends to infinity integration of xn dm. So that is 1 because it is 1 for all n, this is 1. If we now ask, what happens if I just consider limit of xn and then integrate? Okay, so I am talking about can we interchange the limit and integration, these two operations. Okay, so let us see what happens. So for every omega, okay, which is more than 0, so I write which is more than 0, I would always be able to find out 1n such that 1 over n is less than omega, and then consider that type of n. So n is such that 1 over n is less than omega, then xn of omega is 0 for all n greater or equals to capital N. That implies that xn of omega converges to 0 for all omega greater than 0. Measure of the set on which xn converges to 0 is equal to measure of open 0 to 1 closed, but that measure is 1. So that means xn converges to 0 almost surely. Okay. However, integration of the limit, so 0 is the limit of xn, okay, almost sure limit, okay, almost sure limit of xn. So integration of limit of xn is 0 because integration of 0 is 0. So this implies that we are getting this is 0, which is not equal to this 1 because it is not equals to limit n tends to infinity integration of xn dm, correct? So here limit and integration does not interchange. Okay, there is another example. So example 2, consider full R, okay, and Lebesgue sigma algebra and Lebesgue measure here, and we ask that we consider the simple the indicator function 0 to n 1 over n, okay, that is my xn of omega is this. Okay, fine. So here let us calculate what is integration of xn dm, again using the property of integration. This would be 1 over n times the measure of the base where it is 1, that is n. So this is 1 for all n. However, if we consider where does it converge, okay, so for every omega, if it is less than 0, so it is xn of omega is 0 all the time, so it converges to 0 anyway. But if omega more than 0, so there is some n such that xn of omega would be it would be positive. However, as n tends to infinity, okay, so 1 over n, okay, so xn of omega is always less than 1 over n, okay, does not matter, okay, even if it's positive is less than 1 over n, and this dominating sequence goes to 0, so xn also goes to 0. So for all omega positive it is true, and omega less than 0 it is already 0 all the time. So for in general I can write down this for all omega in R. Okay, so this is pointwise convergence. Every point it is converging here. So if you write down limit xn. Okay, so limit xn is 0. If I integrate limit of xn dm, so I am going to get 0 only. Integration of 0 is 0. Okay, so which is not matching with limit of integration of xn dm. So these are the two examples where we have seen that limit and integrations cannot be interchanged. Okay, so one should then ask that under what condition it can be interchanged. Okay, so this is called bounded convergence theorem. This is basically saying that these two examples have two anomalies. If we can avoid both, then actually limit and integrations can interchange. What are the anomalies? First example, there the function was not bounded function because it was for any finite number, positive number, whatever say c you take, okay, a very large number, 1 million, you can always find out one n such that which is more than 1 million, and then that for that particular n, xn would cross that particular number for some omega, okay, for some omega, and the measure of that omega is also positive. Okay, so if this xn, so contrary to that is the xn is bounded. Okay, so if xn is a bounded sequence of measurable function, okay, then I do not have that problem. However, here our xn was a bounded sequence because mod of xn is less than or equal to 1 for all n is bounded. However, that the set of omegas on which xn is non-zero, that set is going to infinity because close 0 to n, and n is becoming larger and larger, so it is becoming the total whole positive real line. So if we also avoid this, what does it mean? That measurable function and the measure what we are talking about is a finite measure, and the mu of omega is finite. That means the totality has finite measure. Okay, and then integration. So here xn is from omega. Okay, then xn d mu limit this is equal to integration of limit xn. Okay, also I should also assume that xn has a limit. If xn is a bounded sequence of measurable function, this also and xn converges to x pointwise. Actually, I don't need pointwise. I mean, converges in converge almost everywhere is also sufficient. So then this is true. Okay, so this is called bounded convergence theorem. There are some generalizations of bounded convergence theorems, many generalizations, important generalizations. One is called dominant convergence theorem. There you do not say that okay, xn is a bounded sequence, like less than some fixed number, but you say xn is mod of xn is less than or equal to another function, measurable function, non-negative measurable function, which is integrable. Okay, then also you can have the same assertion. There are many other generalizations also. We are not going to the details of all these, but this is the basic fundamental result for convergence of integrals. Okay, and then the conditions under which we can put the limit of limit inside the integration. Okay, so next we see one more important result that is important when I have two different measure spaces. Okay, so like but those, I mean, two different measures on the same measurable space, and that comparison between these two measures. Okay, So let us go to the next slide. Consider I have a measurable space omega f, and I have two different measures on this. So mu1 and mu2 are measures on this omega f. We would call mu1 is absolutely continuous with respect to mu2 if mu2 of A is equal to 0 implies mu1 of A is equal to 0, where A is from F. Okay. So what does it mean? That if there is any set A, measurable set A, such that it is null in the sense of mu2, okay, it is measure 0. So then under mu1 also it is null. Okay. So any set which is unimportant with respect to mu2 is also unimportant with respect to mu1. Then we say mu1 is absolutely continuous with respect to mu2. Okay. If that is the case, then we have a very nice result. Okay. Before stating the result, let us see some examples. Okay. So some examples where this property is true. Consider a non-negative bounded measurable function f from omega to r. Okay. And consider a measure space omega f, this omega, and then measurable with respect to this sigma algebra f, and mu2 a measures. Define mu1 of A is equal to, so define for all A in F, integration of f d mu 2 over the set A. Okay. So I have a bounded non-negative measurable function f that I am integrating over the set A with respect to the measure mu2, and whatever the value we are going to get, that we are declaring as the mu1 measure of set A. Okay. So is mu1 a measure? Yes, it is a measure, because for measure you need that measure on empty set is 0. It is true, because if you integrate this function over empty set, you are going to get 0. And then if you ask that, okay, if measure of disjoint countable union of sets is the sum of the measure, that is also true, because if you have disjoint union here of the integration, that you can write down as sum of different integrations, and then from there you are going to get it. So mu1 is a measure, and then if we have mu2 of A is 0, then this is a 0 measure set and this is F. Okay. And now what is the meaning of this integration? This meaning is we take supremum of integration of simple functions, sequence of simple functions which converge, which increases to f. Okay, converge increases to f. However, when we do this, so then integration of A f d mu, which is that supremum of all these A f n d mu, where f n are non-negative, and simple, and increases to f. If we do this, then we see that for every simple function fn here, when you integrate over set a, which is measure 0, I would always get 0 here, because simple functions are summation of ci and indicator functions, finite thing, and then whatever indicator functions we have, but only on the set a, and then base, that base would be of measure 0. So this is 0, supreme of 0 is 0, so this is 0. Okay, so what does it mean? It means that mu2 is equal to 0 implies mu1 of a, which is defined by this, is 0. So it implies that mu1 is absolutely continuous with this to mu2. Okay, so now one can ask that, this is an example, correct? This is just an example of a pair of measure where one is absolutely continuous with another. One can ask that, is it the all class of measures which are absolutely continuous with respect to mu2? I mean, does it mean that any mu1 which is absolutely continuous with respect to mu2 can be written using this way? Okay, so this is a reverse direction question. Okay, so we go to the next slide. So this theorem is called Rad R-Nikodym theorem. So I am not proving it, I am just stating this theorem, Nikodym theorem, that says that, of course, I mean, the statement is not as general as we anticipate. It needs some conditions on the measure. We need sigma finite measure. Okay, what does it mean? That this, even if the measure of the whole set is finite, however, the whole set can be written as a countable union of subsets, and those sets has finite measure. Okay, so the situation when you have a measure space such that the whole set omega can be written as a countable union of, say, finite measure sets, then we call that measure space as sigma finite measure. Okay, so we consider sigma finite measure here. So assume that omega f is a measurable space and mu1, mu2 are sigma finite and mu1 is absolutely continuous with respect to mu2, then there exists a non-negative measurable function f such that mu1 of a set A is integration of f with respect to mu2 over the set A. Okay, so this is the statement of Rad R-Nikodym theorem, and here whatever that f, okay, we obtain. Okay, so this f, if we just change this f at one single point or maybe countable single point, we are going to get another function, but both the functions would have the same integration values. So we are going to take equivalence classes of f. Okay, so take, say, we say f, okay, if f is equal to g almost everywhere, okay, almost everywhere, then we say that we set f equivalent to g. Okay, so this is equivalent class, and then equivalent relation, and then equivalent relation puts one, partition in the class of all such functions, all measurable functions, and then a class of that. Okay, so we denote that box f, okay, is the equivalence. So this is equivalence relation, equivalent relation, and this is the equivalent class containing f. So so then this equivalent class of f is called d mu 1 d mu 2. So this class is called the Rad-Nikodym derivative. Okay, sometimes we do not always mention equivalent class, we just say this function, we understood it. Okay, so this is like, you know, sometimes, you know, this is not specified explicitly, but all the time it is understood that we are talking about the equivalent class. Okay, and this is unique. This is unique in the sense that if f and g are in two different equivalent class, okay, then we would not be able to have this relation for both f and g, or in other words, if f and g are two different functions satisfying this equation for all possible a in f, okay, then f and g should be in the same equivalence class, and that is unique, and that unique class is called the Rad-Nikodym derivative. So we call this Rad-Nikodym derivative of mu1 with respect to mu2. Okay, Rad-Nikodym derivative of mu1 with respect to mu2. Okay, so this Rad-Nikodym derivative, so what is the notion or what is the meaning of that? Because see, if you now replace f here by d mu1 by d mu2, then you can see some algebra is happening what you have visited in schools also, like, you know, so d mu2 and d mu2 cancels like that, d mu1 and d mu1 of a, mu1 of a is, anyway we know that it is d mu1, that we know very well. Okay, so that is the reason of this notation. Okay, since mu1 of a is d mu1 of a, okay, integration of d mu1, okay, over set a, and then that is the reason that we write down f as d mu1 and upon d mu2. Okay, this is the notation. Okay, thank you very much.